Hey, so this is a problem we did some time ago in class. This was number 15 from chapter 8.2. Probably should write chapter 8.2 in here. And we're asked to find the surface area of rotating this curve about the y-axis from these x values. So to do that, we need to consider the following surface area formula. S is equal to 2 pi integral from the bounds, their x bounds, times x, and then times the function, well, the square root of 1 plus the derivative of the function squared. Derivative of this, let's just call it y prime for now, squared dx. Now, if this looks a little funny to you, it's because this is a different version of rotating about the y-axis, but it's one of the versions that we can use. So let's try this out. We write some things a little differently. Of course, y prime is going to be, if you bring the 3 halves down, the 3's cancel. So you get 1 half x to the 1 half. 3 halves minus 1 is 1 half. Okay, and then that's squared. And then this is to the 1 half power. Just writing the radical as 1 half power. Integral is still there, nothing's changed there. 2 pi still on the outside. Sorry about the glare. And let's see. What happens? Well, if you square each of these, squaring 1 half is 1/4. Squaring x to the 1 half is just x to the 1. And that's still all to the 1 half power. And this is just a simple u substitution, actually. Let's see, can we do, we can either do u sub, we can actually even do by parts. Let's try by parts, actually. Let's do this by tabular, shall we? So let's see, for tabular, let's go off to the side a little bit and try and see how this can work. Let me just shoot this over on the side like that so you can see. So we have a derivative column and an antiderivative column. The derivative column is going to start off with this part of the product, x. Its derivative is eventually 0, derivative is 1, derivative of that is 0, so we just keep deriving, keep finding derivative, keep differentiating, however you want to say it. Here we're going to antiderive this one, so find the antiderivative of this guy. And this is just going to be, believe it or not, if you treat this as x, this is x to the 3 halves, because 1 half plus 1 is 3 halves, divided by 3 halves. So it's 2/3, the same inside, to the 3 halves. But by chain rule, you have to divide by the derivative of the inside. Derivative of the inside is 1/4, so divide by 1/4, which is just multiplying by 4. If we do that yet again, we're going to add 1 to the power to make it 5 halves. Multiply the reciprocal of this to what's already there, so that's 2/3 was already there, so we're multiplying by the new power, reciprocal of the new power, 2/5. Inside stays the same. We have this 4 that was already there, but then by chain rule again, we get another 4. There's a lot going on, but I'll simplify it when I write it together. Hope it comes out okay in the video. Multiply these, and then alternate the signs accordingly. And let's come back this way and let's see what we get. So we can see both on the same screen, maybe. I guess it's fine. So, right, so I'm going to write, this is going to be 8/3 x. 1 plus 1/4 x to the 3 halves. And then minus 1 times that. Oh, geez, what's that? So that's 4 times 4 is 16. That's 4. 4 times 16 is 64. So it's going to be minus 64 over 15. And then that's 1 plus 1/4 x to the 5 halves. Then we have to evaluate this whole thing because we anti-derived essentially using this tabular method. Evaluate between 1 and 12, and then multiply by 2 pi after the fact. Perfect. So let's plug in 12, shall we? Let's see. So plugging in 12, we get 8/3 times 12, plus 1 plus, let's see, 1/4 times 12 is 3, so 1 plus 3 is going to be 4. So that's 4 to the 3 halves. Minus 64 over 15, and again, that's going to be 1 plus 3, which is 4, so it's 4 to the 5 halves. This is the first result, plugging in x equals 12, minus, when you plug in x equals 0, Well, that's 0, so that's good. When you plug in x equals 0, that multiplies to 0, so that's fine. Minus 64 over 15 times. When you plug in 0 here, that's just 1. So it's 1 to the 5 halves, which by the way is just 1. And then finally multiply this whole thing by 2 pi. So we're almost running out of space here. I'm at the very, very bottom, but I think we're okay. It's just number crunching at this point. So there's a lot of number crunching actually. So let's see, 3 goes into 12 4 times. 4 to the 1/2 is 2, and then 2 to the 3rd is going to give you 8. So I'm going to cross that out. Hope we can make that out. So altogether this is 8 times 8 times 4. So that's 64 times 4, that's going to be 256. Minus, well, again, 4 to the 1/2 is 2, and 2 to the 5th is 32. And then whatever 32 times 64 is, which I can't do that fast in my head. So I'm just going to write it as 64 times 32. And then when you distribute the negative, this becomes positive, so plus 64 over 15 times 1. And that's all times 2 pi. Now, of course, the way we got this was 4 times 64. So notice they all have 64 in common. So we pull out 64. Pulling out 64, multiplying it by 2 will give us 128 pi. And when you pull out 64, this becomes 4, because you're dividing it by 64. That would be 32 over 15, so minus 32 over 15. Plus 1 over 15. Now, of course, we could write 4 as 4 over 1 to get a common denominator. And then when you multiply 4 over 1 by 15 top and bottom, you get 60 over 15. So altogether on top, we get 60 minus 32, which is 28, plus 1 is 29. So the whole thing will end up being the following answer. 128 times 29 pi over 15. Now, if you actually multiply 128 and 29 together, you should get 3712. So the answer should be 3712 pi all over 15. And there we go. All on one nice piece of whiteboard here. And I hope it was okay to follow. Again, we did this one in class. It's just kind of like a test, actually. Again, there's a glare. Sorry about that. I'm going to work on that. But aside from that, there's that problem. Any questions, let me know. See you soon.